Okay, we have one more example here in section 3.8 on related rates. Example 49. So let's read that together. We have a police cruiser approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is zero point 0.6 miles north of the intersection and the car is zero point 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of the measurement, what is the speed of the car? Seems very confusing, but draw yourself a picture, okay? So the first thing we have is the police cruiser is approaching from the north, a right-angled intersection. So here's the intersection, using it as the origin here. Police cruiser is coming down, great picture of a car, right? Police cruiser is coming down, approaching this intersection from the north. So I'm going to label the distance, since I'm on the y-axis, from the origin, the intersection, to the police cruiser as y. And I know that that y is changing with time. Okay? So y does change, right? As a police cruiser, this y gets smaller and smaller and smaller. So the rate, dy dt, would be negative because it's decreasing. All right? And then we have a speeding car that is running away from the intersection. Okay, so here's the speeding car. It's going away from the intersection. So I'm going to call the distance from that intersection or the origin to the speeding car x. I know that dx dt, the rate of change of that speeding car, would be positive since it's increasing. Okay, so then I have a triangle where I have this side labeled x, this side labeled y, this side labeled x. So I'm going to call this side s, just because I don't want to write d and then take the derivative of d, makes it confusing. So just call it s. So in other words, I have a right triangle where one side's y, one side's x, and the hypotenuse is x. S. Okay. So what do we know? We have three variables, right? S, y, and x. So what do we know? We know ds dt, the rate of change of the distance between the police cruiser and the speeding car, is 20 miles per hour, right? It says the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So this ds dt is 20. Right? We also know that the cruiser is moving at 60 miles per hour at the instant of measurement. So that means dy dt would be minus 60, right? The minus means it's decreasing. Speed is just the absolute value of that, so that's how you get the 60 miles. You're told the cruiser is moving at 60 miles per hour. So what we want is, what's this dx dt? What's the speed of the car? That would give us the velocity, so we just take the absolute value of it. Although we know that will be positive because dx dt is increasing. Okay, so I need a relationship between s and x and y. Hopefully you recognize that right away as, let's use the Pythagorean theorem, right? So s squared equals y squared plus x squared, right? Right here. S squared equals x squared plus y squared. So if I solve for s, I get s equals the square root of x squared plus y squared. And since I do know dy dt and ds dt, I don't need to find another relationship here. So I just get s as one variable of x. One variable, x or y. I don't need a relationship between x and y because I do know a lot more about x and y. I know dx, I know dy dt, I know x, I know y. I'm told at the moment that the distance between the police cruiser and the intersection is 0.6 miles, right? And the car, so x, at the moment that x is 0.8 miles, the car is speeding away 0.8 miles to the east. So I know x and I know y, and then I know dy dt because I know the police cruiser is minus 60. So all I want is dx dt out of that, so I can actually get that. So how do I do that? I start with my equation. I take the derivative with respect to t of both sides. So that's simply ds dt on this side. Now this is x squared plus y squared to the 1/2 power. So I have to use a kind of an inside double chain rule here, right? X squared plus y squared to the 1/2. So I take the derivative of the outside first. I get 1/2 times x squared plus y squared to the minus 1/2. Then I got to take the derivative of the inside. Take the derivative of x squared and y squared. Remembering that both of these are functions of t, time. So the derivative of x squared is 2x, as far as the derivative of the outside, times the derivative of the inside, which is dx dt. The derivative of y squared is 2y, times the derivative of the inside, which is dy dt. So this 2 would cancel with these two 2's. So I'm just dropping those. And then I have 1 over the square root of x squared plus y squared, because that's what x squared plus y squared to the minus 1/2 is. And I'm left with times dx, x dx dt plus y dy dt. So I want to solve for dx dt. Remember, that's what you're asking for. What's the velocity, or actually for the speed of the car that's racing away from the intersection? I want dx dt. So rather than do some algebra up here, I'm going to plug in the numbers first. We know ds dt is 20, right? We know that x is 0.8. We know y is 0.6. So we got 0.8 and 0.6. We know dy dt, the speed of the cruiser, the velocity actually, so it's minus 60. Okay, and then you just want dx dt. So now we have a simple algebraic equation to solve for dx dt. You go through that and you see that dx dt is 70. Since that is not a negative number, I don't need to take the absolute value to make it the speed. That's also the speed, 70 miles per hour.